Okay, today is the day when it starts to get kind of real with the thermodynamics. So everything we've done so far has been warming us up, no pun intended, for this. Okay, what we want to do is we want to learn how to take heat energy and convert it into useful work energy. And the basic idea is as follows. We're going to imagine that we have a piston, which is really just, we have a cylinder full of gas and then another cylinder that kind of blocks the gas from getting in or out. So we have this, actually, hold on, let me make this, I'm going to try to make this a little bit cleaner with nice, okay, so we've got something like this. And there's some gas that is bouncing around. Oh, that's the right way to do this. Okay, it's bouncing around down there. And now we take some heat and we add heat. So when we add heat, what happens is those particles start bouncing around faster and faster. That creates a higher pressure. And this piston, which is this sort of object, maybe make that look a little. So it's kind of, a plug. It's going to move. It's going to move up a certain distance. And that distance, I'm going to use a slightly different color for kind of the gas that fills that space. Okay. So this space gets filled with extra gas. So as this happens, maybe the piston is connected to some kind of a rod or something, and that rod is connected to a wheel, and so it's going to turn the wheel, and it's going to move the car or the locomotive engine or something. And once it moves enough, then we remove some heat, and as we remove heat, well, then this piston, it's going to move back down, and it's going to make the wheel keep turning. And then we add heat, and then we remove heat. We add heat, we remove heat. And if we keep doing this process, we can make the wheel start turning and make this thing, travel down the train track. So how do we characterize this work? Well, we know that work is force times delta x. That would be kind of the simplest way we could say it. And the force is going to be really given by the pressure of the gas times the area of the face of the piston. But the area times delta x, where delta x is how far the piston moves, the area times delta x would be just a change in volume. That would be this yellow volume that I have here, the sort of new volume where we expanded into that space. And so the work is equal to the pressure times delta V. All I really did here was I changed variables into fluid variables. Instead of force and a motion, a change in x position, we have a pressure and a change in a volume. Of course, we know that the force wouldn't necessarily be constant during this process. As the gas expands, the pressure is likely going to go down, and so we don't want this formulation. We want to rewrite it as a more sort of calculus savvy formulation. So we'll write it instead of, you know, pressure times delta V, it's differential work is pressure times differential change in volume. And then we integrate both sides. So the work is equal to the pressure times the, or the integral of the pressure dV. And in general, the pressure is going to be a function of the volume. It might be a constant function, in which case it pulls out and we get back to P times delta V, or it may be a complicated function of the volume. So when we do this, it takes us a certain amount of heat. And we have here kind of a heat input. And then we have a heat output. This heat output is sort of waste heat. That's like the exhaust pipe, the tailpipe of the car, where, you know, hot gases are coming out of that tailpipe. If you ever have the car running for a while, don't touch the tailpipe of the car. It's going to burn you. It's very hot. So most of that heat, in fact, most of the heat we generate when we burn the fuel just comes out as waste heat. And a small fraction of it actually is converted into work. And that's really where the magic is going to happen for us. We want to try to understand this process so we can try to figure out can we maximize the amount of work we get out for the amount of heat that we put in, keeping in mind that the heat output, that's just wasted. Now, you can do clever things, like you can have a machine that's having waste heat run through a water tank and heat water so that, you know, you have hot water for your building. Okay, if you know that you can try to find other uses for that heat, but generally you cannot. So we don't count it when we're talking about how good or bad an engine is. Okay, so any questions so far? Okay, let's just then, if we're going to be doing an integral of pressure as a function of volume, we need to look at graphs of pressure versus volume. So if I have a particular gas, and maybe the pressure is 3 atmospheres, and it's starting off with 2 liters of gas, and then it's under high pressure, maybe we have this piston kind of locked in place so that it can't move. We've built up the pressure, and now we release the piston, we let it move, but maybe there's a constant weight just sitting on top of this piston so that there's a certain amount of pressure on the piston. So it's going to expand under that constant pressure up to maybe, let's say, 6 liters. And we want to know how much work it does. Well, it's very straightforward because we just find the area underneath this graph, and since it's an easy graph, it's a rectangle, I know the area is just base times height. So we want our units to work out and give us joules. We better convert the ATMs into pascals. That would be 3.039 times 10 to the 5th pascals. And 2 liters is 0.002 cubic meters, and 6 liters is 0.006 cubic meters. So, you know, we have conversion factors for those things, and as long as we know, you know, are given the conversion factor, we shouldn't have any trouble with those conversions. Then the work is going to be just the base, which is 0.006 meters cubed minus 0.002 meters cubed times the height, which is 3.039 times 10 to the 5th pascals. Remember, a pascal is a Newton per meter squared, so the units here work out to be Newton meters or joules. And I get 2,087 joules. Okay, so that's a process, a thermodynamic process, but this alone does not make an engine. This would be kind of like if I let the piston expand, I let the gas expand, the piston goes up, and my wheel gets a half or a quarter turn, but then it just stops. So if I want to repeat this process, I need to get it to go back to where it started. Now we could just crank it back. We just push it back. If I push it back, then it requires an amount of work equal to 2,087 joules. And I didn't really get anything out of that. It doesn't do me any good. If this thing, I put the heat in, it expands, it does 2,087 joules of work, and then I spend 2,087 joules of my own energy to crank it back, you know, to its original volume. That's not really very good. Okay, so that's not what we want to do. What we would like to do is crank it back, but at a lower pressure. So the next thing I do is, before I crank it back, I allow it to cool off. And as it cools off, let's say we started at a point A, then we went to point B. I cool it down to point C, which is at 1 atmosphere of pressure. And now I can crank it back at a low pressure. When I do that, the work that it costs me is, you know, much less. And at the end, once I've cranked it back to the small volume, I start adding heat again. And as I add heat again, the pressure goes up, but I have cleverly locked the piston in place so it doesn't start moving as I add heat. I lock it in place so the pressure can just build up again. And then once I get back to point A, everything is exactly the way it was at the beginning. So this truly makes a cycle, which is something that I can repeat. I can repeat it over and over again. Now, what's the net work output going to look like? Well, this was my work output. And my work input was this red area. That's going to be 0.004. That's the width times the height, which is 1 atmosphere, 1.013 times 10 to the 5th. And that's going to be 405.2 joules. So the net work, you can say sum of the works, or maybe just call it the net work, is, well, okay, so the work input, it's technically a negative number, right? Because that's me doing work on the gas instead of the gas doing work on me. So when I add these two numbers up, I get 1,680, let's just round it to 2. So this would be an engine that every time I run it, I get a net of 1,682 joules. And it's repeatable. I can just keep adding more heat. And every time I do it, it's going to go through this cycle. There's going to be waste heat. I don't know yet how to compute how much heat it took me to accomplish this task. It might take me 100,000 joules to get this to happen, which would mean this is not a very good machine. But maybe it only takes 2,000 joules to get it to happen. Then it would be a very good machine. If I got 80% work output for the heat input, that would be incredibly good. I would quit working right now if I had that engine. I would quit this job. And I love this job, but you know. Okay, so that's the basic idea. That's what our target is. We want to be able to understand this. Now, I drew a very simple cycle, you know, with straight lines because it's easy to compute, but we're going to get into more complicated cycles with lines that are not straight, and you know, where we really have to do integrals and more realistic engines. But our end goal is to know how to take any cycle we see, and by cycle I mean a closed loop in the PV diagram, and find the net work output, find the net work heat input, and find the efficiency of that machine. Now, let me draw your attention to something here. When I found the net work, I basically took the black area that goes from underline AB and I subtracted the red area that's going from C to, I didn't label it, but C to D. And so essentially this part of the area just cancels out. And all I really got was the area enclosed by the cycle. And that's generally true no matter what the shape of my cycle is. Suppose I have a cycle that does something like this. So when I compute the work, I'm going to get, some positive work when it's moving to the right, and I'm going to get some negative work when it's moving to the left, and the positive work and negative work partially cancel, leaving only the area inside this closed loop. So in general, we can say the work for a cycle is just equal to plus or minus the area enclosed. It's plus if the cycle is clockwise. For a clockwise cycle, the positive work always overshadows the negative work. But if I would run the cycle counterclockwise, what does that look like if I have something going like this? Then the positive area is small and the negative area is large. And when I cancel out, the overlap, I'm left with this red area, this negative area. Okay. So when we go counterclockwise, we still just compute the area, but the work output is a negative number, meaning that would be a machine that does a weird thing. I instead of adding heat to get a work output, I add work to get a heat output. Okay, we'll talk about that machine later on. Right now I'm talking big picture. All right, now in order to really analyze an engine, in order to know how much heat it takes to do a process, we have to recognize that we're changing the energy of the gas. And there's two ways to change the energy of the gas. I think maybe we talked about this at the very end of last time. So we have delta U equals Q minus W. So in general, the work part of this, we can get by direct integration. Okay, we can do an integral. The delta U part, this is the change in internal energy of the gas. And we know the internal energy of the gas is just the number of particles times the average kinetic energy. So that's what an average is, right? You take the total energy and you divide by the number of things and you get the average. So working it the other way, if I have the average, I multiply by the number and I get the total. So that average kinetic energy, as we learned last time, is 3/2 K Boltzmann times T. And so this is U. And we could re-express this in terms of the ideal, the chemistry version, which would be 3/2, and we would have little n times R times T. So that's the formula for U, and delta U then is 3/2 times n times R times delta T. So we have a formula for delta U, and we have a formula for W, and we kind of get Q by sort of process of elimination. It's not exactly the right term, but we have to find delta U and find W, and then we use that to find Q. And each process, then, it's going to be totally different. However, for every process, delta U is always the same formula. So this is, note, this is always the formula for delta U, except for one factor, which is this 3/2. So we talked about that 3/2. We talked about it when we were doing the the equipartition theorem, and we were learning about the average kinetic energy. And I told you at the time that the language is weird. We say that there's 1/2 k Boltzmann T kinetic energy per degree of freedom, and there are 3 degrees of freedom. And I promised that I'll come back to that and explain that in more detail. What does that mean exactly? And today's the day that we get to see that. So let's talk about a helium atom. Helium is monatomic atom, just a little like a little ball. And in 3-dimensional space, if my helium atom is just at the origin, it can be moving in the x direction, in the y direction, or the z direction. That's the 3 degrees of freedom. Now, what if I have, so that's, helium. What if I took hydrogen molecule? So hydrogen molecule might be kind of looking like this. So there's a little bit of separation between the 2 atoms. This would be H2. So the hydrogen can move in the z direction or in the x direction or in the y direction, just like the helium. But it can also move in different ways. The hydrogen can, well, it can do this. I'm on the wrong layer here. It can start doing that, okay? And as it rotates, there's kinetic energy associated with that rotation. Now, it can rotate the way I just indicated. It's rotating about the x-axis, but it could also rotate about the z-axis. However, if it rotates about the y-axis, we'll take a look at my stylus. It can rotate, x-axis comes out at you guys. So it can rotate about the x-axis, okay? It can rotate about the z-axis. But if it tries to rotate about the y-axis, nothing happens, okay? Those first 2 rotational modes, those are additional degrees of freedom. What that means is when I start adding heat to the gas, some of the heat goes into regular kinetic energy, motion in the x direction, the y direction, the z direction, but some of it goes into making the particles rotate. So if I have a diatomic molecule, it costs me more money, more energy to raise the temperature than for a monatomic molecule, because some of the energy that I put in goes not to the translational kinetic energy, it goes instead to the rotational kinetic energy. So what that means is, to kind of bring it back to this formula, we could, just for like easy practice, we could look at a cycle that's a triangle. So that's not a realistic engine. Nobody makes an engine that has a process, a PV diagram that looks like a triangle, but it's easy to compute the area of it. So it's a good kind of test case to learn how to do things before we get to complicated cycles. Okay, so the 4 processes. The first process, this is the easiest process, is known as isochoric or isovolumetric. Not actually sure which of these your textbook chooses. They're probably equally common names. I prefer the second name, isovolumetric, because it gives you a better clue what it's talking about. So do you guys know what iso means? Like in math or chemistry, you have like isotopes or isomers or isosceles triangles. Iso, anyone know what iso means? This means the same, the same. So isotopes have the same number of protons, but different numbers of neutrons and things like that, okay? So isosceles triangle has two sides that it's the same. So isovolumetric means same volume, or in other words, it's a constant volume process. If we draw the diagram, PV diagram, it's a vertical line. It could go up or down. It doesn't matter up or down. Those would both be constant volume processes. And what's special about the constant volume process is that the area underneath a vertical line, you know, that would be the work. What area do you get underneath a vertical line? It's 0, right? There's no area underneath the vertical line. So we can say the work just equals 0 for an isovolumetric process. That means, using the first law of thermodynamics, delta U equals Q minus W. Since the W is gone, it's 0, we can easily find a formula for Q. Q is just equal to 3/2 NR delta T, or 5/2 NR delta T, depending on if it's a monatomic gas or a diatomic gas. Now let's kind of analyze this formula and compare it with our other Q formulas. You remember from last time that we used to talk about Q equals MC delta T. That's the one. I didn't spend a lot of time on it. I just wanted us to be familiar with it. But in chemistry class, some chemistry class, you spend a lot of time talking about warming up water or cooling down steam. And what's in this formula? Well, there's 3 terms. There's one that's M, how much stuff you have. Well, we have how much stuff you have in this Q formula also, but it's just number of moles. We're not measuring it per kilogram, we're measuring it per mole, but it's still telling us how much stuff we have. We also had delta T. Well, we have delta T in this formula as well. And finally, we have specific heat, which is a constant that tells you how much, you know, heat it takes you to raise the temperature of a certain amount of stuff by a certain, you know, degree. We have a constant, right? The constant C. In this equation, we also have a constant, either 3/2 R or 5/2 R. So really, this is the same kind of thing where the 3/2 R or the 5/2 R is taking the place of the specific heat. So for that reason, we rewrite this as N times C sub V, that's a capital C. The specific heat in the old formula was lowercase. This is a capital C, where the C sub V stands for specific heat at constant volume. And its value, to sort of save ourselves from having to write 2 different formulas all the time, we just say that CV is equal to either 3/2 R or 5/2 R, depending on what kind of gas. We just kind of remember that the CV has, instead of having to look on a table where every single material has a different specific heat, little c, we see the CV and we know, okay, if it's a monatomic gas, it's this. If it's a diatomic gas, it's this. And I don't want us to miss the fact that this is actually kind of remarkable, that we now have a theoretical prediction for the specific heat. This number over here, the specific heat of water or lead or aluminum, that was just data. Those were data. But this is a theoretical prediction. No experiment has been done. And yet, I'm about to show you a table of data for specific heats. And we're going to see that this is a remarkably accurate formula. Okay, it's very impressive, and it's really a triumph of this point of view that temperature is a measurement of the kinetic energy of particles. If we had the caloric theory of heat where there's just a mystical fluid, we never would have a prayer of making a prediction. What is the specific heat of helium going to look like? What is the specific heat of hydrogen going to look like? Or why are they different? Okay, there would be no way to understand that with the sort of older model. Okay, so I don't want to show you the data quite yet. I want to show you the second process, and then I'm going to show you data for both of those processes at once. So my second process is called isobaric. Does anyone have an idea what isobaric might mean?
Is it same pressure?
Yeah, it is, right? It makes sense because, barometer has that kind of bar in it. So this is a constant pressure process. If we draw the PV diagram for this, it's just a horizontal line. We've already seen a process like this. And we know that the work for this process is just the area under this straight horizontal line. That's just going to be P times delta V. And so to find Q, it's delta U plus W. That's going to be N. Okay. When we did Q, we said it's either 3/2 R or 5/2 R. Since we now have a constant that sort of does that, it just does exactly that, we can say that the Q is N times CV times delta T. But here's where students get confused a lot. I'm using the formula for delta U. So let's go back to our delta U formula. We can say it's all, not that. We can just say delta U equals 3/2 CV, sorry, N CV, sorry, just N, not the 3/2, just the N CV delta T. We can say that this is always true. Now the CV takes on either a 3/2 R or a 5/2 R, depending on what gas we have. But the confusion comes because I just told you that this CV stands for specific heat at constant volume. And when we're talking about the formula for Q, this is only a valid formula for Q because if it's isovolumetric, because only for the isovolumetric process is Q equal to delta U. So the CV implies constant volume, but only when we're talking about the Q formula. When we talk about the delta U formula, it does not matter if it's constant volume or constant pressure or constant this or constant that. Okay, so we have a Q formula for the constant pressure process. Unfortunately, this doesn't look the way I'd like it to look. I'd like it to still kind of be in terms of a change in temperature. This is how much Q I have to supply to change the temperature by a certain amount. So we're going to do a little bit of black magic to fix this equation. I'm calling it black magic because my thermodynamics professor made a comment once that stuck with me, that a lot of the math in thermodynamics looks a little bit like black magic. There are a lot of tricks and weird things that you do, and somehow it works, but it can mystify you. This isn't really one of those, but I like that comment. I like that terminology. So here's the idea. I want to see how P times delta V relates to a delta T. So we take the ideal gas law, PV equals nRT, and we differentiate it, okay? So if I differentiate it, I use the product rule, and I get P dV plus V dP equals nR dt. I can think of this Q as a differential form too. I can think of a dQ, which would be N CV dt plus P dV, if I want to write it in a differential form. And here I have P times dV. Now, since this is a constant pressure process, the derivative of the pressure is 0. The pressure is constant, so the derivative of the pressure is 0. And so this tells me that P dV is equal to nR dt, and I can substitute it. We get N CV dt plus nR dt equals dQ. So dQ equals N times CV plus R times dt. And if we integrate both sides, we get, Q equals N times CV plus R times delta T. Okay, so what I did is I used kind of a differential form to see how does a change in volume relate to a change in temperature. And this is what happens. P times delta V would be equal to NR times delta T. But I did it in a differential form because we know how to do derivatives. And it's possible that maybe there's a dP and a dV and a dt. They might all change. And so we have to be able to do the product rule to get this right. And that means derivatives. Okay, now, again, we finally have the Q formula in a format that looks like how much stuff, N, times a constant, specific heat, times delta T. So this constant, CV plus R, we can relabel it and call it CP. That means the specific heat at constant pressure. And it's equal to the specific heat at constant volume plus R. Specific heat at constant pressure, CP. In fact, we can write it for our equation sheet, CP. So if CV is 3, if we have a monatomic gas, we have 3/2 R plus R, which is 5/2 R. Or if it's diatomic, we're going to have 5/2 R plus R, which is 7/2 R, if it's diatomic. So we could say that CP equals either 5/2 R or 7/2 R. So for an isobaric process, the delta U formula is the same as it was for the isovolumetric process. It's always the same formula. But the Q formula is similar, but with a different specific heat. Why is the specific heat higher at constant pressure than at constant volume? Remember, let's make it real again. What is specific heat telling us? It's telling us how much heat does it cost me to raise the temperature by 1 degree. This is telling me that if I have a constant volume process, that every joule of heat that I put in goes to raise the temperature. That's very efficient. I have a 1-to-1 ratio. Every joule of heat that I put in goes to raise the temperature. However, for a constant pressure process, it's not true. Some of the heat that I put in goes to raise the temperature, and some of it becomes work. So if I want to raise the temperature, I have to add more heat to account for the energy lost in doing work, if I want to raise the temperature by a like amount. That's why the specific heat is higher at constant pressure than at constant volume. So let's take a look at some data. Okay, so here's a table. These are data. CV for a monatomic gas our theoretical prediction is 3/2 R, which is 1.5 times 8.31. And that's 12.47 joules per mole Kelvin. And notice for all of my monatomic gases, the data round to 12.5. I round to 12.5 also. The CP is going to be 5/2 R. That's 2.5 times 8.31. And that's 20.78. Again, it tracks very nicely with my data. Now, it should be the case for diatomic that CP is 5/2 R, which would be 20.78 joules per mole Kelvin. Should be exactly the same. Sorry, CV, I meant to say CV. CV for the diatomic molecule is the same as CP for the monatomic molecule. So these should be the same, and they're close, but they're not exact. It means there's something wrong with this model still for diatomic molecules. We will talk about what that is. For CP, we have 7/2 R, which is 3.5 times 8.31. That's 29.1. And we can see that it's close. Okay, so why is it not quite right for diatomic gases and it's perfectly spot on for monatomic gases? Well, that's a little bit hard to explain. I'm just going to give you a sense of why it is, but you've got to take a few more years of physics to actually really like calculate why it's different. It has to do with quantum mechanics. You guys know about quantum mechanics a little bit from chemistry class. When you learn about energy levels of atoms, that the electron can only occupy certain energies, certain orbitals. That's quantum mechanics. It means that the energy can't just be anything it wants. There's only certain states that are allowed. So what happens with diatomic gases is, okay, they rotate, but they don't, if they have low enough energy, that rotational mode doesn't happen. It needs a certain amount of energy to be able to start rotating. That doesn't make sense for a regular barbell shape. If I just throw a barbell into the air, it would be impossible for me to get it to fly with the translational kinetic energy and not get some rotational kinetic energy. It would be spinning a little bit. I couldn't, no matter, even if I try to build a machine that throws it, it's going to be very hard for me to get that to happen without it spinning a little bit. But for an atom, if it's under a certain amount of energy, then it just doesn't rotate. It's either zero or like a certain minimum, and then it goes up in sort of increments. So when we have a gas that's diatomic, remember that all of the particles are not moving the same speed. Most of them are in the vicinity of VRMS, but some of them are much, much slower, which means they're much colder in a sense. They have less energy. And so some of those particles do not rotate. And when we take data, we're averaging over the particles that are really cold and the particles in sort of the medium range of temperatures where they all rotate. And then at even higher temperatures, they can start vibrating like a spring and mass system. The atoms in the molecule can start to oscillate back and forth like they're connected by a spring. That gives us even more modes of, degrees of freedom. So we can even, for example, for O2, we get a little bit too high of a value because some of the particles in O2 at the temperature range that these data were taken have started to vibrate. Okay, so at any rate, I'm just giving you a sense why it's not perfect, but it's very well understood why they are not exact. And it has to do with the distribution of velocities and quantum mechanics. At any rate, this is a very, very accurate and successful theory. And for monatomic gases, there's just no room for other degrees of freedom. They don't start vibrating because there's not two things to vibrate, and they don't start rotating because it's just like a sphere. So there really is no room for extra degrees of freedom, cold or not cold. And so it's pretty much perfect for monatomic gases, and it's very close for diatomic gases at sort of typical temperatures. If you get cold, when the temperature gets cold, then the diatomic gases start to look just like monatomic gases. Okay? We'll just use these values of 3/2 R and 5/2 R and 7/2 R exclusively, and we don't have to look at a table. So, okay. Let's take a look at our last two processes. So the next process is known as isothermal. Anyone have a guess what isothermal might mean?
The temperature is constant.
Yeah, temperature's constant. So if we wanted to know what this looks like on the graph, it's at first glance, it's hard to see. How does temperature fit? How does temperature fit when there's no temperature axis? So anytime we feel like something's missing, though, we have sort of this ace up our sleeve. That's the ideal gas law. So we know that PV equals nRT. So if the T is constant, well, the N and R are both constant as well, we have PV equals a constant. So this curve looks something like that. It's kind of like saying X times Y equals 1. That's the same kind of thing, which is Y equals 1 over X. So it looks kind of like a 1 over X kind of curve, except it's not 1 over X, it's nRT over X, whatever nR and T are. So in this case, the delta T is equal to 0, and that means delta U is also equal to 0. Remember, internal energy is the temperature, is the kinetic energy of the gas, and if the average kinetic energy doesn't change, then the total energy doesn't change either. So, or we could just see it from the standpoint of the formula. If the delta T is 0, the delta U must also be 0. So in that case, the first law becomes pretty simple. Delta U equals Q minus W, and the delta U is 0. So Q just equals W. Now here, to find W, we have to actually integrate this thing. So we've got one point, we're going to another point. The first point has coordinates V1 and P1 and, kind of a hidden T1, and a V2 and a P2 and kind of a hidden T2, but the T1 and T2 are the same. So when we do the integral of P dV, we're going to go from V1 to V2. And we need to know exactly the functional formula for P, and that's where the ideal gas law comes in. We know that P is just nRT over V. So we have the integral of nRT dV over V, and the nR and T are all constants. So this is equal to nRT times the integral of dV over V from V1 to V2. And that's an easy integral, right? Integral of dV over V is just the natural log of V. So we get nRT times the natural log of V2 over V1. You guys know your logs, right? If I have natural log of V2 minus natural log of V1. It's better to express it as a natural log of the quotient. In fact, I've probably mentioned this before, but you cannot just have natural log of V2 by itself because V2 has units. You cannot have natural log of something with units. Okay, it doesn't make any sense. What's a natural log of a liter? Doesn't make sense. So we really have to have it as a ratio. This V2 over V1 has no units at all. Okay, so that's the work, right? That's my work. And therefore Q is also equal to the same thing, nRT ln of V2 over V1. So how do we get something to be isothermal? I don't know if I've talked about that enough with these other processes. Let me just say them briefly. If we want something to be constant volume, we just kind of lock the piston in place. We freeze it. We lock it in place and we add heat. And as the heat goes in, the pressure goes up, but it's not allowed to expand. How do we get constant pressure to happen? Well, it just expands under a constant load. My favorite example, sort of household physics, you can do this, is you take like a bottle, like a empty bottle of some sort, and you put a balloon over the top, and then you put it in a pot of boiling water. And the heat goes in, and as it goes in, the gas wants to go up in pressure, but because of that balloon, the balloon just starts stretching and makes sure that the pressure inside the bottle and outside are always the same. So that's a constant pressure of 1 atmosphere. As the balloon expands, the volume is going up. So for isothermal, people sometimes get this a little confused and they think that to make something constant temperature, we want to insulate it. That's not true. We insulate stuff to keep it at constant temperature when the pressure is not changing. Okay, you have a cooler full of a beverage and you want it to stay the same temperature. What's actually keeping it at the same temperature is the water and ice in the cooler, which are at a constant temperature. And the heat exchanges between the water and ice and your beverage to keep them in equilibrium. So what we actually want to do to make something isothermal is we want it to have a lot of heat transfer. We want heat to flow easily from the system to its environment. We usually do that by making a thermal bath. So that could be just a large volume of water, ice water, so that the water stays at constant temperature, or a large volume of boiling water, so the water stays at a constant temperature, or just plain old a large volume of water because water is already very hard to change its temperature. So if you have like a lake and you're running your machine and you have a heat exchanger going into the lake so that everything stays in thermal equilibrium with the lake, the temperature of the lake's not going to change really because the lake's very big. So that's how we get a constant temperature process to happen. We make sure that it's got very good heat flow. It's the opposite of insulation, really. If we would insulate it and then change the pressure, then the temperature is going to change dramatically. Okay, finally, we get to the last one. This one does not sound like the others. One of these processes is not like the other. Adiabatic. So the word itself, the root word a means not, and dia means through, and ba means go. So this literally is sort of Greek for it doesn't go through. So what doesn't go through? Well, heat doesn't go through. So Q equals 0 is what adiabatic means. How do we make sure heat doesn't go through? That's where we insulate it. Okay? We could insulate it. There's two ways to this. We can either insulate or we make it fast. So if it's very fast, there's just not time for heat to flow. So something like firing a gun is an adiabatic process because it's fast. The gas expands so quickly that there's not time for heat to flow into or out of the system. the expansion stroke in a gasoline engine. You have this cylinder full of air, you inject some gas into the cylinder in sort of a vapor form, spark plug ignites that gas, and there's sort of a little explosion. Boom, the cylinder is shot out of that, the piston is shot out of the cylinder, not all the way out, but shot upward or outward, and that expansion is so rapid that there's no time for heat to flow in or out. So the heat that's in there, we're creating that heat with the ignition of the gas. That's not what Q is talking about. We're talking about, does heat like penetrate the walls of the cylinder? So that's how adiabatic works. If we want to know how to graph it, we need to learn a little bit more to help us visualize. Let's go back and look at isothermal just for a second. And so the constant temperature curves are these hyperbolas. And we could imagine the space being kind of filled with hyperbolas, where maybe that's 100 Kelvin and 200 Kelvin and 300 Kelvin, 400 Kelvin, 500 Kelvin. So basically our graph is, it's P equals nRT over V. So the constant is nRT. The bigger the constant, the farther this graph gets from the origin. So the bigger T is, the farther the curve gets from the origin. So what we can do to visualize adiabatic is we can start off by drawing these isothermal curves. These are known as, just isotherms. And then we look at what the temperature does when the adiabatic process does work. So we have delta U equals Q minus W, but the Q is 0. So that means as work is being done, as we move to the right, the delta U is negative. So this thing is getting colder as it expands, and it has to look something like that. Okay, it looks a little bit like an isothermal curve, but it is steeper because it is losing temperature. Since there's no heat sent in, as the work is done, where is the energy coming from to do that work? Well, it has to come from the internal energy of the gas. So the gas has to get cold because it gives up energy to do the work. And there's no heat input to balance things out. So, but exactly the shape of it, that's a little harder to figure out, okay? So we're gonna look at the first law of thermodynamics in the differential form. So the delta U, we're gonna make that a du. du equals minus dw. And the du would be n CV times dt. And this is equal to minus P times dV. So we're writing everything in the differential form. We cannot find the work because we don't know the function. So we cannot write just the work, but we can write P dV and then try to figure out what that looks like. So now we want to solve this by integrating, but it's a little bit confusing because we haven't really put in how P and V and T are all related. Now, normally when we have something like this, a differential equation that we want to solve by just integrating doesn't work most of the time, but it can work if we only have 2 variables and we can separate those variables. Here we have 3 variables. dt is related to the temperature variable, P is pressure, dV is related to the volume. So that's 3 variables. We need to work it down to 2 variables only. So to do that, we use the ideal gas law, PV equals nRT. That's our secret weapon. We differentiate both sides using the product rule on the left. Again, that's P dV plus V dP equals nR dt. And I can eliminate the n dt that's in my first law of thermodynamics. I have an n times a dt. So n times dt would be equal to p dv plus v dp all over r. So we're going to get cv times p dv plus v dp all over r equals minus p dv. Okay, so let's try to rearrange things and separate our variables. So we have this constant cv over r times p dv plus cv over r times v dp, and we can add a p dv to both sides. And so we have two different terms that have p times dv. So p times dv factors out, and we have cv over r plus 1 plus cv over r times v dp. Now, to try to make the algebra a little nicer, I'm going to multiply both sides of the equation by r. So when I do that, the cv over r just becomes r, or sorry, it becomes cv, and the 1 becomes an r. So what we get is p dv times cv plus r plus cv plus, not equal, cv v dp equals 0. Now, cv plus r is just cp. So we have cp times pdv plus cv times vdp equals 0. And I want to separate the variables. So I'm going to divide both sides by v and both sides by p. So I'm just dividing by 1 over pv on both sides. The right-hand side, of course, nothing happens. On the left-hand side, we get cp times dv over v plus cv times dp over p. And one last step, just to combine these two constants into one, we can divide both sides by cv, so we get cp over cv times dv over v plus dp over p. And now we can integrate the equation. The integral, when we do the integral, we're going to get an arbitrary constant out. Okay? So what else do we get? This cp over cv, it's customary to combine those into one constant and call it gamma. So gamma is defined to be cp over cv. So an equal sign with 3 bars means it's defined. It's just a definition. We just define gamma to be that. So what we get then is gamma times the natural log of v plus the natural log of p plus a constant equals 0. And we can combine the gamma and the v. When we have gamma outside of a natural log, when we have a constant in front of a natural log, what can we do to simplify that? Do you guys remember that from logs? Feel like a log of b, or b log of a, I think is how your math book usually says it. B log of a, what is that equal to? So ln of what? It's rusty on your logs. So it gives you the natural log of a to the b power. Okay, so if you don't remember your logs, you should probably review them a little bit for this unit because there's a lot of logs going on. Okay, so then gamma ln of v is equal to ln of v to the gamma. And we can just move that constant to the other side. I don't know if that constant's positive or negative, so it's just, it's still just a constant. And finally, we can combine these two natural logs. A sum of two natural logs is a natural log of the product. And we can exponentiate both sides. So e to the ln of v to the gamma p gives me v to the gamma p, and e to a constant is still just a constant. So the way we typically see this written is just p v to the gamma equals a constant. Okay, so that's the shape of this curve. P v to the gamma equals a constant where gamma is a number bigger than 1. Remember, gamma is Cp over Cv. And Cp is always bigger than Cv, no matter what kind of gas we have. So gamma takes on one value for monatomic atoms and one for diatomic molecules. Okay, so and PV to a power bigger than 1 is a curve that it drops off faster than a PV to the 1 kind of curve. All right, so those are our 4 building blocks. Now we're going to do a practice on a very easy cycle so we can find out not just the work output of the cycle, but also the heat input and ultimately the efficiency. So suppose we have just a very simple rectangular cycle. We probably wouldn't build this thing, but it's useful to play around with. So we have points A, B, C, and D, and we're going to just say maybe, I don't know, I'll use big numbers, okay, so that the numbers are easy. So just 1 meter cubed and 2 meters cubed. And then this will be, 1.013 times 10 to the 5th pascals. And this one can be 4.052 times 10 to the 5th pascal. So basically it's 4 atmospheres and 1 atmosphere. And suppose the initial temperature is 300 Kelvin. And we want to find the network, the heat input, and the efficiency. Okay, so first of all, network is the easy one. That's just the area. It's going clockwise, so it's a positive area. And that's the base times the height. So the base is just 1 cubic meter times, let's see, the height from 1 atmosphere up to 4 atmospheres is 3 atmospheres. So that's, well, the difference between these two numbers, 4.052 times 10 to the 5th minus 1.013 times 10 to the 5th is going to be 3.039 times 10 to the 5th. So okay, so that's an unrealistically large volume, but it doesn't matter because we're just trying to learn sort of a process here. Okay, now we want to find the heat input. Now there's technically 4 segments, 4 processes, A to B, B to C, C to D, and D to A, but not all of them represent heat going in. So I'm going to teach you a trick to find when is the heat going in and when is the heat going out and when is there no heat. Okay, and the trick involves kind of drawing in some isothermal lines. Okay, so we can visualize what's happening with the temperature. So for example, from point A to point B, I know that these red lines are always increasing temperature as we move farther from the origin. So from A to B, I know the temperature is increasing. Does that make sense? You guys, are these lines making any sense to you yet? Can we see if this is the closest to the origin is the first line, so it must be the coldest, and the next line must be warmer, and then warmer still, and then warmer still. So when I go from A to B, I'm moving up across two lines, so I'm getting hotter. Okay, so what we're going to do is we know that delta U equals Q minus W. And so Q equals delta U plus W. We're going to make a little table. We're going to have delta U and W and Q. And we're going to have each segment AB and BC and CD and DA. And what we're going to do is we're just going to analyze the signs only without computing any numbers. The signs only of delta U and W and use that to find the sign of Q. So going from point A to point B, we already said the temperature goes up. And if the temperature goes up, that means delta T is positive and delta U is positive. So we get a positive sign for delta U. Whenever the temperature goes up, internal energy increases. Whenever temperature goes down, internal energy decreases. How about from B to C? What's happening to the temperature? Is it going up or going down or staying the same? From B to C, the top line. Come on, if I made this extra credit, you'd all turn it in. It would be the easiest extra credit of your life.
Going up.
It's going up. So the sign of delta U should be positive. Okay, from C to D, what's happening to the temperature? You can just show me with your thumb. What's happening with the temperature? Going down, right? So we get a minus sign. And for D to A, what does temperature do? Goes down. Okay, good. So we've got the signs of delta U. That's easy. Once we have those isothermal lines in our picture, it's very easy to tell. The only one that wouldn't be easy is if it's diagonally down to the right. You know, I can't tell if the temperature goes up or down from B to D because I don't know that my red lines are accurate. I don't know they're accurate. So, you know, it's possible that these lines should have been much steeper. But that's, sometimes you don't know, but most of the time that's enough to tell. How about the sign of the work? What's the sign of the work going from A to B? Is it positive or negative? You didn't realize that's a yes or no question. Is it positive or negative?
It's 0.
So the answer is no. It's not positive or negative. It's 0, right? It's not positive or negative. It's 0. Why is it 0?
Because it's isovolumetric, so there's no area under the line.
Right. So I was kind of offering you a little bit of a trick question when I said, is it positive or negative? It was a bad question. It's 0. There's no work going from A to B. How about the sign of B to C for the work? Is this, when it goes from B to C, is that an example of the gas doing work on us, or where we would get a positive sign, or is it an example of us doing work back on the gas, where we would get a negative sign? Sophia says up, I think that means plus, positive. Yes, that's right. It's positive work done by the gas. Whenever the gas expands, it's doing work. Whenever it contracts, we're doing the work. So that would be negative work by the gas. How about the work from C to D? 0. Okay, and from D to A, it's negative. Okay, great. So once we know the signs of delta U and W for a process, we can determine the sign of Q for the process most of the time. Okay, let's look at A, B. We're getting Q by adding delta U and W. When you add a positive number and 0, what do you get? You get a positive number, right? Has to be. What do you get when you add two positive numbers together? Positive number, right? Okay, fill in the last two signs. So when we do a negative and a 0, what do you get? Fill that in on your own. Should be negative. And two negatives make a negative, right? Who thought positive when I said it? Come on. I know it happened. You're used to your math teacher saying two negatives make a positive, right? So that's true if we're multiplying, but if we're just adding them up, two negatives still make a negative. Yeah? I just wanted to throw that one out there because it could, later on, you could think I'm multiplying. Okay, I'm not multiplying, I'm adding. Okay, so we know the signs of all of the Q's. I only care about the Q when it's positive. That's the heat going in. So what this has told us is that there's QAB going in, and then QBC going in, but then the QCD is going out. And the QDA is also going out of the gas. And when we're computing the efficiency of an engine, we don't care about the waste heat, even though that's most of the heat oftentimes. We just care how much heat's going in. So that's, by doing this little exercise, it saves us time. We don't have to compute all four of those numbers and check which Q's were positive. We already know which ones to compute. So QAB is, well, what type of process is AB? I can hear you thinking it. It's isovolumetric. Okay, so the formula for Q, since it's a constant volume process, it's going to use the constant volume specific heat. All right, so we have a couple of choices here. We can try to use the number of, figure out the number of moles. All right. Did I say what kind of gas it is when I started? I don't think I did. So let's just say it's diatomic. Okay, just, so that we can figure out the value of CV that we want to use. We can just find the number of moles using the ideal gas law, or we could try to convert this formula using calculus. I'm going to show you the second way, but probably you're going to want to use the first way. I'm just showing it to you because maybe when you take thermal later, it might be useful. So we have kind of dQ equals NCV dt. And then we take the ideal gas law, PV equals nRT, and we differentiate it. But we can differentiate it saying to ourselves that the volume is constant on this process, right? On A to B, the volume's constant. So when I take the derivative, this is just dP times V equals nR dt. So what I could do is I could replace, the N and the dt with dP VdP over R. And that means that V times delta P over R equals N times delta T. So I could rewrite this as CV times V delta P over R. Okay, if I do that, I never have to find the number of moles. I don't care what the number of moles is. However, I've got a lot of experience with students, and I know most students prefer to just find the number of moles. So let's see how to do it this way, and then we'll find the number of moles anyway. And for the next one, we'll use the number of moles. So CV for diatomic is 5 halves R times V delta P over R. So the R just cancels out. And we have 5 halves times my volume, which is 1, times the change in pressure. That change in pressure is the same, change in pressure we computed there. It's 3.039 times 10 to the 5th. So this is going to be 7.6 times 10 to the 5th joules. Okay, if we wanted to find the number of moles instead, we would say the number of moles is PV over RT. That's just a rearrangement of the ideal gas law. And I could pick any pressure, volume, and temperature I want and work that out. Now, what's the advantage to what I just did is that I don't need to know the temperature at point B by doing what I just did. Let's see what the number of moles is. That would be 1.013 times 10 to the 5th. I'm just going to pick point A times 1 over 8.31 times 300. It's going to be a very large number of moles. Maybe not very large, but large. So 40.6. So if I use the number of moles, I have to find out also delta T, which means I have to find the pressure or the temperature at point B. How do I find that? Well, I use the ideal gas law again. Okay, so this is how I would suggest doing it. If we want the temperatures, we would say PV equals nRT, and I'm going to put it at point B, and then PA VA equals nRTA, and just divide those equations. When I do, number of moles just cancels out. The volumes are the same at point A and point B, so those cancel out. And TB equals TA times PB over PA. So that's 300 Kelvin times 4 atmospheres over 1 atmosphere. I think that's what I had, right? 4 and 1. So I was going to write it in atmospheres since the units are going to cancel out anyway. We find out the TB is 1200 Kelvin. So I could also say QAB equals, NCV delta T, and that's 40.6, I think that was my 40.6 moles times 5 halves times 8.31. And my delta T going from 300 up to 1200 is 900. And I get 7.6 times 10 to the 5th. Joules. Okay, as I said, we could do that either way by finding the number of moles and finding the temperatures. That's perfectly fine. That's what students like to do because it's the task is well defined. But I personally think this other method is way less work. It's less work for me. When you take thermodynamics, you'll probably do it this way. But let's go ahead and find the temperature at point C, since we have the number of moles, and we can find the QBC. So all we do is we write ideal gas law PV equals nRT twice, PV equals nRT. This is one of the reasons that I told you guys to do it this way when you're just doing ideal gas law problems, to get used to this process, because we don't need to find the number of moles and find everything all the time. So the N's and R's cancel. I'm going to put C on top and B on the bottom. And if we look at our process, What's constant about BC? What's constant is the pressure, right? So the pressure is the same between point B and point C because we have a horizontal line. So that means I can just cancel out those pressures. They are the same. And TC is equal to TB times VC over VB. So that's equal to 1200 Kelvin times my VC is 2 and my VB is 1. So that's 2 over 1. That gives me 2400 Kelvin. So I picked really nice numbers so that we wouldn't waste a lot of time with arithmetic here. But in general, if you notice, what happened here is the pressure went up 4 times, so the temperature went up 4 times from A to B. And then the volume doubled, so the temperature doubled. So there's a logic to it. And sometimes, you know, that logic is sort of a quick and easy way to find how the temperature changes. Okay, finally then, QBC is going to be N. This is now a constant pressure process, so NCP delta T. And that's 40.6. My CP is 7/2 R, so 7/2 times 8.31. And then the delta T going from B to C, it went, what was it? 1200 to 2400, so that's a change of 1200. And that is 1.42 times 10 to the 6 joules. Okay, so now we have both of the heats in, and we can find the efficiency. So the efficiency is the work, you know, the net work over the heat input. And my net work was 3.03 times 10 to the 5th, 3.039 times 10 to the 5th. And my Q in is the sum of these other two numbers. So 7.6 times 10 to the 5th plus 1.42 times 10 to the 6th. I get 0.14, which is 14% efficiency. So that's not very good for a car, but there are probably cars out there that are worse than that. I remember when I was in college, I worked night shift in a gas station, and it was in like a small town, so there were a lot of farmers, and farmers come in really early to fill up. So there was a kind of a farm kid. He was like a high school kid, but he worked on the farm like before school, and he would come in every morning with this really big, old beat up like 1970s Ford pickup truck. And I mean, the size of the gas tank was enormous, and the bill every morning, it was huge. And I asked him one day, I said, you know, what kind of miles per gallon you get in that thing? He said 7. That's bad. If you don't know that, that's really, really bad. So, I mean, it probably cost him so much money just to drive into the gas station from the farm every morning. Okay, cars are a lot more efficient now. So cars can do better than this. All right, that's basically, that example is a simplified, you know, it's got all the ingredients, but we used a very simple process, or simple cycle, just isovolumetric and isobaric. Next class, we're gonna sort of break into, you know, more complicated cycles, what an actual cycle in a gasoline or diesel engine looks like, how to find the efficiency, how to find the work, how to find the heat input, all of that. And our ultimate goal is not only to know how that works, but to find theoretical limits for efficiency so that we know when we design a certain engine if it's good or not. Okay, like how good can it get? We cannot get to 100% efficiency for certain theoretical reasons. So let me, since we could probably take another 2 minutes, I want to draw an illustration to sort of give you a different perspective on what a heat engine is doing, and that will help us to recall that picture next class. So here's like just a totally different way of thinking about a heat engine. So imagine we have a hot place, and the hot place, I'm going to put that up on the top. Fill it with red. And then we're going to have a cold place. Down here. We'll fill that with blue. And this kind of, I've done this one time before. I did this, sometimes I do it sideways and it looks like the flag of France, and sometimes I think this is like the flag of the Netherlands or something. Anyway, that's not what I'm trying to get at. What I'm trying to get at is what happens in a heat engine is we've got a hot place with a temperature, we could call it TH, and a cold place with a temperature TC, and then we connect them. Okay, so when we connect them, then what happens is heat wants to flow. It sort of starts to flow from the hot place toward the cold place. That's just nature. Why does it do it? It's just a statistical process. There's no real reason it has to do it. It's just that we get collisions of particles, and when a hot particle and a cold particle collide, the hot one is moving fast and the cold one's moving slow. And odds are, after the collision, the slow one speeds up and the fast one slows down. And so that winds up becoming a net flow of heat from the hot place to the cold place. Now, when we build a heat engine, what we're doing is we kind of build a machine that sits in between here. And we siphon off some of that energy. So we get some work output. So we get a QH, which is the heat flowing from the hot place. That would be my heat input. And we get a heat Q cold, which is my waste heat, and we get work. In that last example, the Q hot was, I didn't get a number for that, did I? Let's find out what that number actually was. So 7.6 times 10 to the 5th plus 1.42 times 10 to the 6th. That's around 2.2 times 10 to the 6. Okay, so we've got 2.2 times 10 to the 6 joules of heat flowing from the hot place into our machine, where we get only 3.039 times 10 to the 5th joules of work. And then our waste heat is the difference between those two. So that's about 1.9. We'll just round this to, we'll do this. We'll round this to 3.0. And then this is 1.9 times 10 to the 6 joules of waste heat. Okay, so that's the picture that we want to be thinking about. This is how it works. Those two heats flowing in, the QAB and the QBC, those are both my Q hot. And the two heats flowing out, the QCD and QDA, those are both the heat going to the cold place. And then the area of that loop is my work. Now, if we were to rotate, if we run the sequence backward, instead of going clockwise, if we go counterclockwise, then everything flips. The work is input, the QC goes the opposite way, and the QH goes the opposite way. And this would be a machine where we spend energy to move heat from a cold place to a hot place. That seems like a weird thing to do, but most of you have a device like this in your home that moves heat from a cold place to a hot place. Does anyone have one of those? Sophia has one. Shema has one. Where do you keep that machine, Sophia?
It's, I think, outside, like, I'm not sure exactly where it's located. I think it's like throughout the house, I guess.
Okay, so you have more than one machine like this in your house. You have one the one you're thinking of is your air conditioner, and you have a heat exchanger outside the house that exchanges heat with outside. That's where your hot place is, and then you have another heat exchanger inside, probably in the basement or something, which is where the cold place is. And that, well, so it depends which way you're doing. So if we're doing air conditioning instead of a heat pump, then we're really the cold place is you're taking heat from inside the cold place, the basement, and you're pumping it to outside, and you're making your house colder. The device I was actually thinking about is a refrigerator, and you keep that in your kitchen probably. It does the same thing. You've got a box, and the box, when the refrigerator's unplugged, the inside and outside are the same temperature. But then you plug it in, and it starts pumping heat out of the inside of the box to the outside of the box. And so the cold place gets colder, and the hot place gets hotter. So refrigerators, air conditioners, heat pumps, all of those are really the same device as a heat engine, but they're just operating in reverse. So we'll also get to talk about that, next week as well. All right, that's it. I'm sorry I kept you a pretty long time today, but I want to make sure you have plenty of juicy material to solve lots and lots of problems over the weekend.